Good evening. Good evening, everybody, and welcome to Drink and Derive, a YouTube show where I will be doing some nice and non-simple mathematical derivations for some of you, simple for some other people, of course, and having a drink. So, over the years, I have had some very good physics teachers, very good maths teachers, at right up to PhD level, some very good teachers, and they will always tell you that the first stage in doing a derivation or solving any problem is to get your pen and paper and draw a diagram. Well, I may agree with them on everything else that they ever say, but I disagree with them on that. Because in my opinion, the only way to be successful at doing any kind of non-trivial mathematics, step one, is to have a drink. Now today's drink is going to be Bianco Martini, and since I've moved down south, I'm kind of allowed to have that. Right, so, without further ado, this week's episode, the Poisson distribution. Okay, so I'm going to talk about the Poisson distribution. Well, we've got to start somewhere. Okay, so what a lot of people you might have come across if you've done mathematics up to A level, that's like AP level in the States, I guess, or like Abitur in Germany. If you've done mathematics up to that level, you've probably come across a thing, well, you might have come across the Poisson distribution. You've probably come across a thing called the binomial distribution. This is a very useful probability distribution. It's the probability distribution that occurs when you take an event which can have two outcomes. So, toss of a coin is a very good example. It can have two outcomes, heads or tails. And if you toss the coin many times, the probability that it lands heads, I mean, at least on an unbiased coin, right? Or, well, actually, not even just an unbiased coin, a coin that's not being controlled by magic. If you toss it many times, the likelihood of getting a heads or a tails result on one trial is independent of all the other trials. Okay? That property is called statistical independence, probabilistic independence. And the binomial distribution applies to things which have two solutions, heads or tails for a coin, and are independent. Trials are independent. And the binomial distribution also just describes this mathematically when there are a known number of trials. So if I take a coin, I toss it 10 times, and what I want to ask is, say, what is the probability that if I toss a coin 10 times, that I will get heads 3 times? Okay? Right. Now, so the mathematics of the binomial distribution looks very simple. Probability that x equals r. So in this case, the x is the random variable. That is how many heads we get out of a certain number of coin flips. R is the number of heads we're looking for, so in this case it'd be 3. We're going to write it generally, the formula generally. Now I'm going to make this P kind of capital, because otherwise it'll contrast with the later one. First thing is P to the R. Now, so what this is saying is, if the probability of me getting heads is little p, that's what that is, little p, probability of one successful trial. If the probability of me getting heads is 0.5, that's p, little p, and I want 3 heads, then obviously, if I was just doing that, heads, and then another heads, then another heads, statistical independence, that would be probability of heads 0.5 times 0.5 times 0.5. Right, so this first term is kind of obvious. If I have a fixed number of trials, and this is what I said, the binomial distribution is for a fixed number of trials, say 10, okay, then if I have 3 heads, that's p to the r, then every other time I must have thrown not heads. Probability of not throwing heads is 1 minus p. And the number of times I must have thrown it is n minus r. So I've got this many heads and this many tails, right? And that's kind of the naive thing you would say is the whole story. But there's also this term here, which, I mean, some people write it like this, NCR. And what that symbol represents is the number of ways I can order those throws. So if I want 3 heads in 10 throws, I can have head, 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 and then 7 tails. Or I can have head, tail, head, head, and then or tails, heads, tails, heads, tails, heads, tails, tails, tails. Right. So or many other arrangements, and those are all contribute equally to the probability because they are not the same outcome. Okay, the throws are independent, but the total event includes orderings. And that is the thing you can get out of your calculator, right? So you know, if you just want to do a calculation, it's very easy, but we're going to write it out in full because we're going to do a derivation here. And this is written out in full as n factorial over r factorial into n minus r factorial. Okay? So that, I mean, it may look a bit complicated, but really, it's just saying, you know, how many ways can you order n things? But you can order, you know, you just want r of them, so you're just going to order the order of r. And then how many times can you order the other things? That made no sense, did it? But never mind. And hopefully you know what a factorial is. I mean, I'll probably do a video on that in future. That's one of my little hobbies, talking about factorials. But anyway, basically, if you're not that familiar with the factorial, just think of this as n times n minus 1 times n minus 2 times blah 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 times 3 times 2 times 1 in the integer definition. That's the binomial distribution. Great. It's really useful for calculating how many what the probabilities of getting 3 heads in 10 coin tosses. I mean, it's also used by horse racing people and stuff, right? But actually, it's not all that useful in physics. What's more useful is, I mean, the reason I think it's not very useful in physics is because of this fixed n business, right? If I get 10 trials, well, what if I just have a thing that's just happening? It just carries on happening. I don't know that I'm gonna, you know, if I have 10 atoms and I say how many of them are going to decay in a few minutes, well, fine, but I have loads of atoms. Okay, so we need another distribution that can deal with what we might call continuing processes. And that distribution is called the Poisson distribution. And yes, that is the French word for fish. I think it's just named after a guy called Mr. Poisson, Mr. Fish. I mean, that's not an uncommon surname anyway, is it? Right, basically, we're going to make this thing useful by saying that we're going to take the number of trials to infinity. Infinity is always a very scary thing to write down. And you shouldn't really think of it as infinity, just think of it as continuous. So it's a process where the number of trials is just going to keep happening. It's going to keep happening, okay, until you like. Okay, and P is going to go to 0. Well, okay, that's a bit weird, because I mean the things are still going to happen, right? What this is called the this is, well, I mean, some people call this the law of large numbers, right? It's like we're going to have an event that is tested a lot of times, but is actually quite unlikely. Okay, the real magic here is what we're going to do is we're going to say that n times p remains finite. It's going to remain finite as this number lambda. Okay, now infinity times 0. You see that product in the limit can be whatever you like. We're going to take it to be lambda. Right. And basically, to enforce this condition, what we're going to do is we're just going to take this equation, binomial distribution equation, and we're going to replace either n or p with some expression involving lambda. So you can replace n or you can replace p. Have a look at that. See which one you think. Yes, now unless you want this to get very involved and nasty and far too hard for someone not very clever like me, you are going to choose to replace p. So, the probability that x equals r is equal to lambda over n to the r. You see, all we've done there, right, is we've just taken this and we've said that lambda over n is therefore equal to p. Right? Okay, times 1 minus lambda over n to the n minus r times n factorial over r factorial times n minus r factorial. Great. Job done. Poisson distribution derived. Let's go home. Well, unfortunately, it's not quite that simple. Alright, moving on. This is the major trick here. Major trick I'm going to do. It's not even difficult, but this is the thing. Okay. You just split up this power like that. So something to the power of a minus b is equal to something to the power of a divided by something to the power of b. And that's, you know, pretty basic mathematical fact you should have learned pretty early on. This is really what's going to make it possible for us to do it, right? So we need to do that. The next thing we're going to do is write out this factorial. n minus 1, n minus 2, and then a load of other rubbish, right? 3 times 2 times 1. Okay, over r factorial, great, right. We're going to leave that one, because, you know, I mean, you wouldn't know, but I've done this a couple of times, right? We're going to expand this one, 3 times 2 times 1, yeah? Oh, bugger, I've used... No. Never mind. Anyway, what you can see now, okay, is a couple of cancellations that are gonna happen. These are really nice. So, you know, really nice. Right. Basically, we said that p was going towards 0, and so lambda over n is a very, very small number because n is a very large number. So 1 minus a very, very small number is still nearly 1, and nearly 1 to the power of anything that's not infinity is still nearly 1. In fact, if this is exactly 1, then 1 to the power of anything is exactly 1. So we're going to say that this is 1. So that's pretty reasonable, right? Now the next thing you can see is that actually, because this n minus r was smaller than n, right? This 1, this 2, and this 3, all of these are going to cancel, right? They're going to cancel all the way up to here. Until you're left with this. It will cancel all the way up to n minus r. And so this will only go down to n minus r plus 1. Right? Now we are really getting somewhere. Okay. Now, I'm going to just expand out these a bit. Now here's the thing. It'll turn out that I want this over somewhere on the left, right? I actually want to keep that. So I'm going to move it down here. So you know this is all times, there's no pluses or anything, so we can do whatever we like basically. Right, so I've got lambda to the r over r factorial. And I'm going to take this n to the r over there in a minute, right? So 1 minus lambda over n to the n, right? And then I'm still left with n into n minus 1 into all that other crap. N minus r plus 1 over n to the r. Now this is where things start to get a bit sketchy, and because I'm not actually a mathematician, and I like to have a drink, don't take any of this as rigorous, but, you know, I'm going to convince you, right? What I'm going to convince you of is that in this series here, we're going down from n to n minus r plus 1, there are r terms. I'll give you a second, right? But it's not that hard to puzzle out that there are r terms in that series, in that product, not a series. Okay, so we've got r terms in there. And also n's really big. N's a much bigger number than r. In fact, n's, you know, big as you like. Huge. So all of these terms are all roughly equal to n. So it's roughly equal to n times n times n times r times. In other words, this is roughly equal to n to the r. So that lot there, that awkward little bastard, is 1. So here we go. Lambda to the r over r factorial times 1 minus lambda over n to the n. That's it. That's the Poisson distribution. We've done it. Or have we? Well, yes and no. In fact, that's true. That's the Poisson distribution, but that's probably not the way you'll see it written down in your textbook. And this bit here, getting to this, is going to be the most difficult part, and that's why I'm going to have a bit more to drink. Right, okay, folks. Here we go. Okay, right, so here we go. I'm going to simplify this thing. Damn, right. We're going to say let's have y equals 1 minus lambda over n to the n. This is the thing we're trying to simplify a bit, okay, until it becomes more familiar to you. And the way I'm going to do this is I'm going to take the derivative dy by d lambda. Right, that's going to be n to 1 minus lambda over n there, to the n minus 1. So we pull that out in front, we take the power by 1, we've got chain rule there. So we've got times by minus 1 over n there, chain rule. Don't ever forget your chain rule. It's important. Right, So in other words, dy by d lambda, you see this n there is going to cancel with that n, right, is minus 1 minus lambda over n to the n minus 1. In other words, well, okay, brilliant. You see where I'm going now? Right, well if not, never mind. Okay. Basically, again, gonna go back to our thing, that n is really, really large number. It's a really big number. And so, n minus 1 is roughly equal to n. Because, I mean, 1's really small, n's really large. Really large minus 1 is still really large. Okay, so n minus 1 is roughly equal to n. And therefore, this dy by d lambda, really roughly, is equal to minus 1 minus lambda over n to the n still. I mean, I've cheated there, right? But all I've done is I've changed n minus 1 back into n, because it's nearly the same thing. In other words, it's roughly equal to minus y, right? dy by d lambda equals minus y. That is quite possibly one of the first differential equations you ever learned how to solve. But just in case it's not become obvious to you, I'll solve it for you now, right? We can take the y over that side. 1 over y dy integral sign equals minus integral sign d lambda. See, all I've done there is a separable differential equation. I've taken d lambda up to this side, taken y over to that side. I've got all the y's on the left, got all the lambdas on the right. Integrate both sides. Right, bingo. Log y is equal to minus lambda plus constant of integration. I mean, you don't care. It's going to be 1, right? Well, it's going to no. This c is going to be 0. It's going to be 0. I mean, just, forget it, right? So y is e to the minus lambda. I mean, I would have hoped that you could have spotted that there, because that's the thing, if something's derivative is equal to the same thing, or just times a constant, it's going to be an exponential. And the old saying is, if something walks like a duck and it quacks like a duck, and if you think it's an ironing board, you've probably had some bad acid. So basically, we've come to the conclusion that 1 minus lambda over n to the power n for really large numbers is e to the minus lambda. Let's go back. So we said that there, right? E to the minus lambda equals, so it's lambda to the r of r factorial e to the minus lambda. And that is the thing you'll see in the textbooks. And hopefully that's helped you out a bit if you needed to do that derivation. If not, then, I haven't wasted my time because I've had a nice drink. And quite frankly, I have nothing better to do than sit here randomly scribbling in this notebook. I'll see you next time.